Cassini-Huygens mission is an international mission between the European Space Agency and the US Space Agency, which has been orbiting around Saturn since July 2004.
On September the 15th, 2017, billions of miles from Earth, a faint stream of data blinked across the deep space network antennas in California, Australia, and Spain. This was Cassini's last transmission, and it revealed a message that NASA never explained.
Orangey, hazy moon. When Cassini was built, we put on spectrometers that could see to longer wavelengths.
NASA's Cassini spacecraft had spent 2 decades traveling through space and orbiting Saturn, sending back discoveries that reshaped planetary science. In those last moments, Cassini dove into the giant planet's atmosphere and transmitted its swan song. Today, we'll unveil the whole story. The story of the Cassini-Huygens spacecraft. In October 1997, after years of planning and international collaboration, NASA launched the Cassini-Huygens spacecraft from Cape Canaveral aboard a Titan 54B Centaur rocket. The mission was a joint project between NASA, the European Space Agency, and the Italian Space Agency, designed to explore Saturn, its complex ring system, and its diverse collection of moons. At launch, the spacecraft weighed more than 5,600 kilograms, making it one of the heaviest interplanetary probes ever sent into space. It carried 12 scientific instruments aboard the Cassini orbiter and an additional 6 on the ESA's Huygens lander, which would later make history by descending through the atmosphere of Titan. Cassini's journey lasted nearly 7 years before it entered Saturn's orbit in July 2004, marking the start of a mission that would redefine our understanding of the outer solar system. This was a historic moment, and it had not come easily. This story cannot be told without first stepping back to understand the moment in history from which it emerged. By the late 1980s and early 1990s, the Cold War-era space race between the United States and the Soviet Union had ended, leaving behind a dramatically different landscape for space exploration. With no geopolitical contest driving the urgency of missions, NASA began shifting its priorities toward long-term scientific discovery and international cooperation. Saturn, long a target of fascination since the flybys of Pioneer 11 in 1979, and Voyager 1 and 2 in the early 1980s, stood out as the next great frontier. Those earlier missions had revealed tantalizing mysteries, such as Titan's thick orange atmosphere, the intricate structures in Saturn's rings, and the possibility of ocean worlds hidden beneath icy surfaces. But they were quick reconnaissance missions, not extended studies. Scientists wanted more than glimpses. They wanted to stay, orbit and probe. In 1982, NASA and the European Space Agency convened to consider a joint planetary mission. Out of those early conversations grew the idea of combining a Saturn orbiter with a Titan lander, a concept that evolved into what would become Cassini-Huygens. The mission reflected a new era in space science, one where collaboration across nations was as important as technological ambition. NASA would build the Cassini orbiter, ESA would design and contribute the Huygens probe to land on Titan, and the Italian Space Agency would provide the crucial high-gain antenna and other components. This was an unprecedented alliance. However, funding for Cassini faced challenges in the US Congress, with critics labeling it too costly. The final mission price tag reached about $3.26 billion, spread among NASA, ESA, and ASI. But defenders argued that the scientific rewards would be immeasurable. By the early 1990s, momentum was unstoppable. Cassini-Huygens was to be one of the most ambitious interplanetary missions ever attempted, carrying state-of-the-art instruments that could study Saturn's magnetic field, atmosphere, and rings with unprecedented precision while also examining its moons up close. On October 15, 1997, after nearly 2 decades of conception and design, Cassini-Huygens lifted off from Cape Canaveral Florida, aboard a Titan 54B Centaur rocket, the most powerful US launch vehicle of the time. At launch, the spacecraft weighed more than 5,600 kilograms, making it the heaviest interplanetary probe ever built. Its sheer size reflected its complexity. Cassini carried 12 scientific instruments, including cameras, spectrometers, magnetometers, and plasma detectors, while Huygens carried an additional 6 instruments designed to probe Titan's mysterious surface and atmosphere. The spacecraft also included one of the largest interplanetary radio antennas ever launched to transmit massive amounts of data across nearly 1 billion miles. But the challenges were far from over. Getting Cassini to Saturn required ingenuity and patience. A direct flight would have been impossible with the available rockets, so mission planners charted a trajectory using multiple gravitational assists. Cassini slingshotted past Venus twice in 1998 and 1999, swung by Earth in August 1999, and past Jupiter in December 2000, using each flyby to build the momentum it needed for the long haul. These encounters also provided opportunities for bonus science. During its Jupiter flyby, Cassini captured nearly 26,000 images and studied the giant planet's atmosphere and magnetosphere. On July 1, 2004, after nearly 7 years and 3.5 billion kilometers of travel, Cassini finally entered orbit around Saturn. Its arrival was marked by a tense sequence of maneuvers, including a 96-minute engine burn that had to succeed or the spacecraft would sail past the planet into the abyss. When mission controllers at NASA's Jet Propulsion Laboratory received confirmation that Cassini was securely in orbit, applause and relief swept the room. This was a historic milestone. Making history in planetary science. Cassini had become the first spacecraft to orbit Saturn. The planet had remained a remote and enigmatic icon in the night sky for millennia. Cassini's arrival also set the stage for Huygens's triumph. On December 25, 2004, the probe detached from the orbiter and began its 3-week journey toward Titan. On January 14, 2005, Huygens descended through Titan's thick atmosphere, parachuting for 2 hours before landing on the surface. The probe transmitted images of river channels, floodplains, and pebbles made of ice, revealing a world eerily reminiscent of Earth, but dominated by liquid methane and ethane instead of water. It was humanity's first and only landing in the outer solar system. The detection of towering plumes of water vapor and organic molecules erupting from Enceladus, first observed in 2005 by the spacecraft's instruments, suggested the presence of a global subsurface ocean beneath its icy crust. This was groundbreaking because it provided the first compelling evidence that a small moon of Saturn might harbor conditions suitable for microbial life. Before Cassini, Enceladus was considered an unremarkable ice-covered body, and no mission had been able to probe its geophysics with such precision. By flying directly through the plumes, Cassini's instruments, such as the ion and neutral mass spectrometer, analyzed their composition, detecting water, carbon dioxide, methane, ammonia, and complex organics. Yes, the very building blocks of life. The mission also transformed our understanding of Titan, Saturn's largest moon, which is larger than Mercury and had long intrigued scientists because of its dense, nitrogen-rich atmosphere. Cassini, along with the Huygens probe, revealed that Titan possesses stable lakes and seas of liquid hydrocarbons like methane and ethane, making it the only other world in the solar system with standing liquid on its surface. Radar mapping pierced the thick orange haze that had obscured Titan from telescopic observation, uncovering vast dune fields, river valleys, and even evidence of rainfall. Cassini also allowed scientists to observe Saturn's atmosphere and ring system in unprecedented detail. Its cameras and spectrometers documented colossal storms, seasonal variations, and atmospheric dynamics that could never have been studied during a brief flyby mission like Voyager in the 1980s. For instance, Cassini captured the massive storm of 2010 to 2011, which wrapped around the entire planet and demonstrated how energy builds and erupts within Saturn's deep atmosphere. The mission also provided high-resolution images of the planet's hexagonal jet stream at its north pole, a geometric weather pattern unlike anything else in the solar system. The rings of Saturn were revealed by Cassini to be complex and ever-changing systems shaped by the gravitational influence of nearby moons. Cassini's instruments measured ring particles ranging from tiny dust grains to house-sized boulders, and it captured striking geometric wave patterns caused by orbital resonances with moons like Mimas and Pan. Before Cassini, such features could only be glimpsed in low-resolution images. Now, scientists could study them with precision. Over its 13 years in orbit, Cassini conducted 294 orbits of Saturn and completed 162 targeted flybys of its moons, returning more than 450,000 images and over 600 gigabytes of data. This immense archive transformed planetary science from static snapshots into a dynamic chronicle of seasonal and geological change in a complex planetary system. Before Cassini, most of what scientists knew about Saturn came from fleeting glimpses during the Voyager flybys of 1980 and 1981, which, though groundbreaking at the time, could not provide sustained, in-depth study. Cassini's longevity made it possible to track changes across years, observing how Saturn and its moons evolved over time. This had never been achieved before for any outer solar system body, but as with all good things, this too came to an end. The end of an era. As the years passed, scientists and the public alike were captivated by the sheer beauty of the images it transmitted. Cassini even detected giant storms on Saturn, including the so-called Great White Spot, a massive storm system that reappears roughly once every 30 years. Yet every mission has its end, and by 2017, Cassini was running low on fuel. Without sufficient propellant to continue adjusting its trajectory, the spacecraft would eventually become uncontrollable. NASA now faced a dilemma. It could leave Cassini adrift and risk an accidental collision with moons like Titan or Enceladus, both of which are considered prime candidates in the search for extraterrestrial life. Even a microscopic amount of Earth bacteria could have contaminated these pristine environments. To avoid this, mission planners adopted a deliberate and dramatic solution, directing Cassini into Saturn's atmosphere. Here, it would burn up like a meteor. Yes, the decision was made to destroy Cassini. The plan, called the Grand Finale, was no simple plunge. Between April and September 2017, Cassini carried out 22 daring orbits that threaded the narrow gap between Saturn and its innermost rings, a region never before explored. Each dive brought the spacecraft within 2,000 kilometers of Saturn's cloud tops and just above the upper edge of the atmosphere, while skimming past the inner ring system at speeds of over 120,000 kilometers per hour. These close passes enabled Cassini to directly measure the mass of the rings, probe Saturn's gravity field, and capture high-resolution data on its atmosphere and magnetic field. The maneuvers were both scientifically invaluable and perilous, since even a small fragment of ring material could have destroyed the spacecraft. On September 15, 2017, at approximately 6:32 a.m. Eastern Time, Cassini began its final descent into Saturn's atmosphere. The spacecraft continued to transmit data in real time, relaying information on atmospheric composition and density as it sped into the planet at nearly 113,000 kilometers per hour. The signal was received by the Deep Space Network station in Canberra, Australia, and continued for about 1 minute after atmospheric entry before the spacecraft was torn apart by increasing pressure and heat. The final transmission, a faint carrier signal, was received on Earth at 7:55 a.m. Eastern Time. After almost 20 years in space and 4.9 billion kilometers traveled since launch, Cassini's voice fell silent. At NASA's Jet Propulsion Laboratory in Pasadena, California, where Cassini had been managed, the operations team stood together as the signal was lost. For many, it was like saying goodbye to a trusted friend. But Cassini's sacrifice was not in vain. In its last act, the spacecraft ensured that future missions to Titan and Enceladus would explore uncontaminated worlds, while also sending back unique data from Saturn's atmosphere that no probe had ever collected before. By the time it was gone, Cassini had completely changed our understanding of Saturn. But what did it reveal in its dying moments? The final transmission. When Cassini approached its final moments on September 15, 2017, it was still fulfilling its role as a scientific observer to the very end. The spacecraft had been instructed to keep its high-gain antenna pointed at Earth throughout its atmospheric entry, ensuring that every last fragment of data would be captured. These final transmissions represented a culmination of 13 years spent orbiting Saturn and nearly 20 years of operation since its launch. In its last hours, Cassini returned high-resolution images that revealed Saturn's rings and upper atmosphere in striking detail. These images, captured by the spacecraft's imaging science subsystem, included close-ups of the planet's cloud tops, showing banded structures and storm systems in unprecedented clarity. Photographs of the rings, taken from inside the gap between the planet and its innermost ring, resolved fine structures down to tens of kilometers across. This was imagery no spacecraft had ever delivered before, and it became part of Cassini's final gift to science. Beyond images, Cassini's suite of instruments continued to operate, capturing data as it plunged into Saturn's atmosphere. The iron and neutral mass spectrometer, designed to measure the composition of gases, provided the first direct sampling of Saturn's upper atmosphere. It measured hydrogen, helium, and trace elements such as methane and water, which are critical to understanding the dynamics of the gas giant's outer layers. Simultaneously, the radio science subsystem monitored changes in the spacecraft's signal as atmospheric drag increased, offering precise telemetry on pressure and density profiles. Other instruments, like the magnetometer and the cosmic dust analyzer, continued transmitting until the last possible second, building a multi-dimensional dataset. The telemetry data were particularly significant. Telemetry is essentially the spacecraft's heartbeat, recording internal health parameters such as thruster firings, temperature, fuel levels, and antenna orientation. In Cassini's case, telemetry also documented the spacecraft's efforts to maintain stability as Saturn's atmosphere pushed against it. Engineers at NASA's Jet Propulsion Laboratory watched the thrusters fire continuously to keep the antenna locked on Earth. These signals were received by the Canberra Deep Space Communication Complex in Tidbinbilla, Australia, part of NASA's Deep Space Network, or DSN. The DSN, consisting of facilities in California, Spain, and Australia, is humanity's communication lifeline with interplanetary spacecraft. For Cassini, Tidbinbilla was the only antenna in view during its final descent, capturing its fading signal with giant 70-meter radio dishes. At 7:55 a.m. Eastern Time, controllers at JPL saw the carrier wave from Cassini disappear from their monitors. The signal had traveled approximately 1.4 billion kilometers, taking 83 minutes to cross the gulf between Saturn and Earth. By the time the loss was confirmed, Cassini had already been destroyed in Saturn's atmosphere. The silence in the control room was broken only by quiet applause and tears. Many of the engineers and scientists had worked on Cassini for decades, some since before its 1997 launch. Among Cassini's last visual data were images that once again highlighted the strange and elegant order within Saturn's rings. For years, Cassini had revealed that the rings were not just random accumulations of ice and rock, but highly structured systems shaped by gravitational interactions with Saturn's moons. In its final orbits, it captured views of spiral density waves and bending waves, patterns that appeared as ripples and geometric arcs across the rings. These were caused by orbital resonances, where small moons exert regular gravitational tugs that shape the distribution of particles. Some waves were linked to moons as tiny as Pan and Daphnis, which orbit within ring gaps only a few kilometers wide, yet create visible signatures extending for thousands of kilometers. The striking regularity of these features gave the impression of intentional design. NASA scientists, however, have consistently interpreted the rings within the framework of physics and planetary science. The density waves, bending waves, and resonance features all arise naturally from the interplay of gravity, orbital dynamics, and particle collisions. Just as tides on Earth are influenced by the moon's pull, the particles in Saturn's rings are sculpted by nearby moons. Even the smallest perturbations can create large-scale order, giving rise to patterns that appear geometric to the human eye. NASA administrators like Thomas Zurbuchen, then Associate Administrator for the Science Mission Directorate, spoke about Cassini's final moments in terms of preserving planetary protection, gathering unprecedented science, and honoring the thousands of people worldwide who contributed to the mission. what NASA said and didn't say. Not every part of Cassini's final transmissions has been widely shared outside academic publications. NASA highlighted striking photographs of Saturn's rings and atmosphere on its official platforms, but most of the spacecraft's raw data were stored in the planetary data system. These included outputs from instruments such as the Ion and Neutral Mass Spectrometer, or INMS, and the radio science subsystem, which produced streams of numerical measurements. For example, INMS recorded counts of hydrogen, helium, methane, and other gases at different altitudes. Telemetry of thruster activity or antenna signal strength appeared as engineering readouts. While publicly accessible, such data are difficult for non-specialists to interpret, leaving gaps in public understanding. Cassini's final moments unfolded exactly as engineers had predicted. On September 15, 2017, at 7:55 a.m. Eastern Time, the spacecraft's signal disappeared, entering Saturn's upper atmosphere at roughly 113,000 kilometers per hour. Cassini used its thrusters to maintain orientation for as long as possible. Within a minute, atmospheric drag overpowered the spacecraft. Its antenna tilted away from Earth, and the signal degraded into background noise. The spacecraft's last datasets were scientifically significant. In 2018, a study led by Hunter Waite and colleagues, published in Science, analyzed INMS readings from the final orbits. These revealed that Saturn's upper atmosphere contained not only hydrogen and helium, but also water, methane, and ammonia, evidence of chemical interactions between the rings and atmosphere. In 2019, another science paper used gravity measurements from the same period to estimate that Saturn's rings have a mass about 15 times that of Earth's moon, suggesting they may be less than 100 million years old. Across its 20-year mission, Cassini sent back over 635 gigabytes of data, including more than 453,000 images. These archives continue to support new research. Studies of Enceladus's plumes rely on Cassini's mass spectrometer readings to refine models of the Moon's ocean and its potential habitability. Titan's methane lakes and seasonal weather, mapped by Cassini's radar and infrared instruments, have informed NASA's Dragonfly mission, scheduled to launch in 2027. Cassini project scientist Linda Spilker emphasized in 2017 that the mission's data would keep scientists occupied for many, many years. The spacecraft orbited Saturn 294 times and completed 162 targeted flybys of its moons before its end. Well, that's it for now. Thanks for watching. Did you like this video? If you did, please consider liking, dropping a comment, and hitting the subscribe button so that you don't miss out on our new uploads. Also, don't miss this video you see on your screen right now. It's truly unbelievable.